This is the last part of the lecture on the properties of the Dtft. In this lecture, the objectives are to talk about and explain the multiplication property of the Dtft and work out some examples. So the multiplication property says that the multiplication of two signals in the time domain, here y of n is x of n times h of n. When you take the Fourier domain, the multiplication becomes a convolution, but here it's a periodic convolution because the signals are periodic in the frequency domain. And the periodic convolution is defined as follows. So the periodic convolution of x times h is the integral only over the integral over 2 pi. You pick an interval of length 2 pi, so typically between minus pi and plus pi of x of ej phi, h of ej omega minus phi d phi. And don't forget the 1 over 2 pi here. So you can think of this as a dual of the convolution property. So we know that convolution in the time domain becomes multiplication in the frequency domain, and also here it says this property says that multiplication in the time domain is periodic convolution in the frequency domain. As an example, let's take the product of two low-pass filters. So in the time domain, as we've seen before, the low-pass filter, the impulse response looked something like this. Again, it's like the sinc function. So here you have a low-pass filter with cutoff frequency 3 pi over 4, and this is the graph of it here. And you have and the second filter has cutoff frequency equal to pi by 2, and this is what you have here. So I'm multiplying these two signals in the time domain. So what's going to happen and to obtain y of n? So in the frequency domain, the response is going to be the periodic convolution of this signal times this signal. So let's do the convolution. I'm going to try to do it in a little bit of details. So I think this is x of ej omega, and this is h of ej omega. And then the convolution here is going to be, which is y of, maybe I'm going to drop, but no. So y of ej omega is the integral of, so I have to decide what to flip. So I'm going to flip the, let's say x. So I'm going to flip and shift the x. So x of ej phi minus omega, h of ej phi d phi. And don't forget the 1 over 2 pi because and the integral here is only in an interval of length 2 pi, so I'm going to do the integral from minus pi to plus pi. And actually I made it, so I mean the way I check if this is correct is that the argument here and the argument here should sum up to omega, and here it doesn't. So actually I made a typo, so here it should be flipped, the sign. So here, because first I have to, so x is a function of phi, so here instead of omega, so here it's omega minus phi. So let's suppose that this is the phi axis here, right? And omega and and you have that here. You're flipping this guy here and you're shifting it. So as it is here, so it's shifted by omega. So when you flip it, is the same because it's symmetric. But when you shift it, so this is omega actually. So in this case, omega is here because I shifted by omega. Right? Now, if you do the multiplication as it is right now, it's 0 if omega is very far. Now, when the multiplication becomes non-zero, when this guy here, let me draw it in blue, when you get to, so you keep increasing omega or decreasing omega this way until this guy here, maybe if I draw it in yellow, it's so here until you hit here. So this is x of, actually this is x of ej phi. So maybe, to be more rigorous here, let me just, it's just, this is a dummy variable, but because we want to reserve omega to y of ej omega, so the dummy variable is phi here. Now, for what value is this, for what value of omega here? You're going to get these two signals touching. So this value here is pi over 2 plus 3 pi over 4. So this is when the first start touching each other. So, and then this would be equal to 5 pi by 4. Or negative 5 pi by 4. Right, because we are in the negative part of the axis, so this is the 0 here. Right, and this is why here you can see that the first thing you start having here, a non-zero component, is when omega, so this is omega equal to 5 pi by 4. Now, once this guy, so once you start moving this guy here, this guy, if you keep moving it to the right, the multiplication is going to be the area of the intersection. So what's going to happen here? So imagine it as a movie. So you're shifting this guy to the right, and the integration is going to keep increasing because so maybe if I draw it here. 1 second, so let me pick the right pen. So if you keep moving it, so I'm going to write, so if you keep moving it here, so the integration is going to be this part here, right? And the more you move it, the more the area is going to overlap, and this is why it's going to increase linearly. This is what you have here, until the whole green circle, the green thing is inside the yellow thing. So until this is the extreme case here, so maybe, so let me do it in blue here. So this case here, this is what's going on in terms of the graph. So you have the yellow thing here that is kind of, you have the green thing that is completely inside the yellow thing. So so it's here. So this is, and the value is here. This is the area. So actually the value here is 1/2 because this is the area that is, actually no, the area is the area of the green thing, and the green thing has height 1, right, and length pi, right, but you have to divide by 1/2 pi, and this is why it's 1/2 here. Now, what will happen next is that you keep moving the the yellow thing. You keep moving it right. So, and as you keep moving it, right. So the whole thing is still gonna be, the green thing is still gonna be inside the yellow thing, and this is why you have the constant part here. So even you keep moving it until the extreme case, which is here, the corner case, is when the green thing start to get out of the yellow. So when this case happens, so you're starting, the yellow thing is starting to exit the green thing, right? And then if you do the calculation, this is going to happen at pi by 4, and here you get the linear phenomena again, because you're exiting, the overlap is decreasing again, so the overlap is going to be, so it's going to be something like this. So this is the yellow, and then in the green thing you're exiting here. So the convolution is this, and the more you move in the plus infinity direction, the more the overlap is going to decrease, and this is why you see here that the value is decreasing. Now, all you need to do here is to realize that the value is 1/2, and just to compute when these corner cases happen, right? And then you know the point. So the first point starts here, because you know that when you are moving, the overlap is going to increase linearly. So you know that the spectrum or the convolution is going to be piecewise linear. So all you need to know are the extreme points. So all you need to know is that when these corner cases happen. So you know that one corner case happens at -5/4, and then if you do the other calculation, you get that you have pi minus pi/4, pi/4, and 5pi/4. And then the values are 1/2. I just showed you how you compute them. So all you have to do is to know these corner point, and then you can join them. So, I mean, by now you should know how to do the convolution, but I just wanted to walk it through with you just to remind you how to do it. Remember that actually what we got the Dtft of y in the interval -pi plus pi, but actually the real thing is gonna be periodic. So what we get is we get these many copies of the of what happened between -pi and +pi, and the Dtft of y is gonna be the addition of these copies. So this is what I got here. So let me highlight it in red. So what we found that I don't know if you can see it. So let me, maybe if I choose a different color, I'm gonna highlight it in green. So here, what we found this guy here, but we know that it's going to be repeated because it's a periodic signal. So what I need to do is I need to do the shifts, and then so I get, when I do the shifts, I get the other copies here, and I know that the real thing is going to be the sum of these guys. So this is the, and then when you sum this part here, so you have one going down, or we have, then the sum of these things are going to cancel each other here. So you're going to get some, so you're going to get something like this when you sum them. It's going to be constant, it's going to go up, and then you're going to get here y of ej omega. So it's the sum of all these copies. This is the sum of all the copies. And the problem is that, like I said, so it's kind of you're going to create some problem here because you're summing these copies and you're kind of losing information, and this problem is called aliasing in DSP, and this is a major issue in DSP. So, and here I have a problem for you to try at home, which is to kind of try so suppose you have two low-pass filters, one with cutoff rate alpha and one with cutoff rate beta, and then the question is to find conditions on alpha and beta such that there is no aliasing in the product of these two things. So this is an interesting problem. So the condition, so no aliasing happens.